Hey everyone, in this video we're going to be talking about compartmental analysis. This carries right over from our mathematical modeling. So compartmental system is one that can be modeled by describing interactions between distinct stages of the process and can be visualized using block diagrams. So here's a one compartment system. We have our input rate, we have some function x of t, and then our output rate. So the input rate gets plugged in into our function and we get our output rate. And so x of t is the amount of substance in the compartment at time t. And so the derivative of x with respect to t would be our rate of change, but specifically the rate of change in the amount of the substance in the compartment with respect to time. So our mathematical model would look like the following. The rate of change, or the derivative of x with respect to t, is going to be our input rate minus our output rate, the rate of change. And so for mixture problems, a lot of times we'll have some kind of mixture problem where we might be mixing fluids in a tank or other substances. You end up having the following calculations. So your input rate is your flow rate times the concentration. And what that ends up looking like is amount over time is your input rate. And the flow rate is a volume over time, and the concentration is an amount over a volume. Okay, so let's look at this example. Consider a large tank holding 1,000 liters of pure water into which a brine solution of salt begins to flow at a constant rate of 6 liters per minute. The solution inside the tank is kept well stirred and is flowing out of the tank at a rate of 6 liters per minute. If the concentration of salt in the brine entering the tank is 0.1 kilograms per liter, determine when the concentration of salt in the tank will reach 0.05 kilograms per liter. So there's a lot going on here, but we're going to figure this out using some mathematical modeling. So first, let's assume that our concentration is kept uniform. That's that sentence about kept well stirred. And so here's our solution process. Let's first define our variables. We're going to let x of t be the mass of salt in the tank at time t. So x is going to be our dependent variable. It's going to depend on our independent variable t in minutes. So we're going to use a one compartment system for the model for this situation. And so first, let's find our input rate. And so remember the calculation we talked about. It's flow rate times concentration. So for input, the input rate is 6 liters, the flow rate is 6 liters per minute, and the concentration of the salt entering is 0.1 kilograms per liter. So we get 0.6 kilograms per minute when we divide out our liters. Okay, now the output rate, let's first determine the concentration. Concentration is amount over volume, and so we don't know the amount of kilograms, so we say x, or x of t, and the volume of the tank is 1,000 liters. Okay, and this is a constant volume, and this is because the input equals the output as far as the flow rate goes. We're having 6 liters pumped in and 6 liters pumped out per minute. And so our output rate would be our 6 liters per minute times our concentration, giving us 0.006 x kilograms per minute. Okay, so first, do we know any initial values? And we do. At time 0, x is 0 because it's just pure salt water, or pure water. No salt has been added at time 0. And so we have an initial value problem. So we have our derivative equals our input rate minus our output rate. And so we just fill in our values. And I went ahead and put the units on there, and then our initial condition. And so notice that the units are consistent. They're both kilograms per minute. And then notice that this is a separable linear equation. And so what we want to do is we want to solve for x of t, and that gives us the mass of salt at time t. And then what we'll do is we'll use the desired concentration to solve for time, because the question was actually asking us about time. So what I'm going to do is I'm going to use our method of finding the integrating factor instead of just doing our nice separable equation calculation. But if you want to double check, feel free to solve it just by isolating your x values on one side and your t values on the other side, and then integrating. So we're going to do our integrating factor steps. So I'm going to write in standard form, so just a little bit of rearranging. And then our integrating factor mu is e to the integral power of p, where p was the coefficient on x, so that's for us 0.006. And then we get our integrating factor is e to the 0.006t. And then remember how this goes. You multiply both sides of your equation by that integrating factor. And then when you do that, that will give you the product rule sort of backwards. So if you take the derivative of this product, you will get what you just had here on the left side of the equal sign. And then you can integrate pretty quickly from there. On the left side, you just integrate the derivative. Those are nice and they undo each other. And then on the right side, we end up with 0.6 times 1 over this power here, 0.006, and then e to that same power, plus our constant c. So we want x, so then just divide by e to the 0.006t. We get x of t equals 100 plus c over e to the 0.006t. And so if the question was just to find a function of involving t, we would almost be done as soon as we find c. But the question was actually about solving for time for a certain concentration. So we have a few more things we need to do. First one is to find c. So using our initial value, plugging in when t is 0, the output is 0, we figure out that c is negative 100. So plugging that in, we get our function x of t is 100 times 1 minus e to the negative 0.006t, and this is kilograms because it's the salt concentration, the mass of the salt. And so now to find the actual concentration at time t, we have to divide by volume because concentration is amount per volume. And so our concentration of our tank was 1,000 liters. So dividing this out, we get 0.1 times our same parentheses here, and this is kilogram per liter now. And now what we want to do is we were asked about a specific concentration, so we need to set our equation equal to that. It was 0.05 kilograms per liter, and our goal here is to find the time when this happens. So we're solving this equation for t. Okay, so we'll just do a little bit of algebra here. We're going to just divide out the 0.1 and then move over some terms, adding and subtracting, and then take natural log of both sides so we can get to the t, which is inside the exponent right now. And then if we just divide, we get t is negative natural log of 0.5 over 0.006, and that's about 115.52 minutes. So I know I went through the algebra pretty quickly, but hopefully you're okay with that, or you can kind of pause it and verify the steps there if you want to spend a little more time on that. And so we have our time when we got that desired concentration. And now let's see, can we validate this? So let's consider what happens when time goes to infinity, okay, of our x of t function. So the limit as t goes to infinity of our function that we came up with would give us 100 kilograms. If you just kind of think about this is a negative exponent, so this would be like 1 over e to this positive exponent. And as this gets really large, because t is increasing, that whole fraction becomes 0. So it's just like 100 times 1. And so for a 1,000 liter tank, the concentration is this 100 kilograms out of the 1,000 liters, which is 0.1 kilograms per liter, which is exactly what we were told in the directions for the question. So this appears valid because the salt concentration levels off to equal the concentration flowing into the tank. So it seems like a valid answer that we came up with using our modeling and our math skills. So now, let's say from this previous example, we want to consider the brine leaves the tank at a different rate. So 5 liters per minute. It's going to get a little bit more involved here. And this time we're going to determine the concentration of salt in the tank as a function of time. So we don't have to solve for t this time around. We're actually just finding a function that's going to tell us about the salt at time t. So our output rate is going to change, not our input rate. Our volume in our tank is no longer constant because we're having 6 liters flow in per minute, but then 5 liters flow out per minute. And so we have our 1,000 liter tank plus think of it as like 1 liter per unit of time. So that's what's happening with our volume. And so our concentration is our amount of salt in kilograms over our volume, which is dynamic here. So 1000 plus T in the denominator. So then our output rate equation is our flow rate of 5 liters per minute times our concentration that we just came up with, and that gives us 5x over 1000 plus T, and that's kilograms per minute. So then our model, same setup, the derivative of x with respect to T equals input rate minus output rate. And so our input rate was the same as before, but our output rate is this new value we just calculated, 5x over 1000 plus T. And then we still have our initial condition. Okay, so this is a linear equation. This one's not separable this time around. And so we are going to go ahead and use our integrating factor again. And so we have just a quick calculation for mu, our integrating factor. We end up getting 1000 plus T to the 5th power. So just going through our steps for what happens with this process, multiply both sides of our differential equation times our integrating factor. Then remember, this left side is the result of the product rule, which would give us this right here. And so the derivative of this product gets us right back what we had over here. And then the next step would be to integrate this. Okay, so we integrate both sides. And remember, what we're trying to solve for is x in terms of t. So we integrate over here. Real quick, if you think about u substitution here, to integrate, you'd have u equals 1000 plus t. But because the derivative of 1000 plus t is just 1, then you don't have to do anything extra with dividing anything out there. And so the integral would just be the same quantity in the parentheses. The integral value would be that quantity in the parentheses to the 6th power over 6. Okay, just reminding you a little bit about your integration rule. And the left side, you integrated the derivative, so those are nice and undoing each other. And so if we just divide out this 1000 plus t to the 5th power, we get our function x of t equals the following. Okay, we do have our initial condition though, so we can find c. So plugging in 0 for t and setting that equal to 0, we can find out that c is negative 0.1 times 1000 to the 6th. This is, you can get this as a number with just like ones and a bunch of zeros, but this is a more condensed way of writing this. Okay, so here is our function. X of t equals 0.1 times 1000 plus t minus all this. And let's just do a little bit more. We wanted this to be a concentration as a function of time, and so we just have to take our result for this is the mass of the salt right here. We need to just divide that by our volume to give it a concentration. So this is our answer. This is a function that gives us the concentration of the salt at a given time t, based on the output rate being 5 liters per minute this time around. Okay, so the last thing we're going to talk about in this section is population models. And so the same idea here that we were talking about, it's just we're specifically dealing with populations. So we have a growth rate, and then it goes into our population modeling function, and the output is a death rate. And so growth and death rates are proportional to present population. So we're going to have a constant of proportionality. And so here's an equation for us. The rate of change, or derivative of population with respect to time, is growth rate minus death rate. And k sub 1 and k sub 2 are constants of proportionality at the present time that the population was observed. And so you can kind of just group those together and then call those k. And so we have a model here. It's called the Malthusian or exponential law of population growth. And we have that the derivative of the population with respect to time, or the rate of change of the population over time, is just k times p. So k is some constant of proportionality. And then at time 0, we have our initial population. We call it just p sub 0 or p naught. And so if you solve this initial value problem, it results in the following. So you would get your population as a function of time equal to p naught equals e to the kt. So this is the initial population times e raised to the power of your constant times t. And now, just a quick note, this model actually only accounts for death by natural causes. And so there's another model, and we'll look at an example of each one of these. It's called the logistic model, and it uses a death rate proportional to the number of two-party interactions. So we're not going to get into all the details here about what all this means. I do just want to show it to you. And so we have our rate of change of our population over time equals negative A times P, which is our population, times quantity P minus P sub 1, or P sub 1 is some other population we know at a specific time, population value, and then our initial condition. And so if you solve this, your logistics function would be population at a given time is equal to the following. Okay, so it's kind of a lot going on here, but notice it has similar components of this nice other model back here. It has e raised to a power involving time, and then something to do with initial populations getting multiplied by that. So this logistics function has a little bit more going on, but it is just a matter of plugging in and solving. In our case, we don't have to do a whole lot of solving our differential equation because we're actually given these models. So let's start with the first one. In 1790, the population of the US was 3.93 million, and in 1890, it was 62.98 million. So a lot of growth in 100 years. So we're going to use the Malthusian model to estimate the US population as a function of time. So let's go ahead and let t represent the first value we have, so 1790, and so that means our initial population is going to be the 3.93. And so we already have our function from our model, so p of t equals our initial population times e to the kt, and we just have to find k. And so we're going to use our other given value for population to do this. So for 1890, that's 100 years later, so time went from time 0 to time 100. And so we plug in 100 for t, and now we know what that equals. It should equal 62.98, and we just solve for k. So we just do a little bit of algebra here. We're going to divide out the 3.93, take natural log of both sides. That's going to give us 100k equals the right side, and if we divide that out, we get that k is about 0.027742. And so here is our population function as with respect to time. So we can plug in time, and we can get a population value based on the time that we've inputted, just from knowing what happened in 1790 and 1890. Okay, so let's do one more, and this time we're going to use the logistics model. So a previous example, same given population for 1790, but now we have another intermediary population given. In 1840, the population was 17.07 million. So the logistic model, we're going to use that to find a function to estimate population at a given time. So the goal is the same, but we're using a different model. So we still are going to say t equals 0 to give us our initial population. And what we need to do for this logistics model is we need to figure out a and p sub 1. Okay, so for 1840, that's 50 years from the starting time. So t is 50. And we know what that equals. It's 17.07 million people. And based on our logistics models that we had written down earlier, we have the following information that we can plug in. So all these 3.93s are what we plugged in for P naught. And then we know that T was 50. So notice it's an equation with two unknowns. A is unknown and P sub 1 is unknown, but we do know what this equals. So remember from algebra, anytime you have two unknowns, you need two equations to be able to solve that. So now we plug in for 1890, time would be 100 there. We know what that equals. We plug in our same P naught values, but now T is 100. So now we have two equations with two unknowns, A and P sub 1. And you can use a system of equations to solve this, or a method for solving systems of equations. These are a little complicated, so you can use a numerical approximation method like Newton's method to solve. But what we're going to do is I'm actually going to show you that this one's a really special, nice case. Okay, and so this system specifically is going to let us use these really nice given formulas, and this is true anytime one of your times is double the other time. So for us, the fact that one of our known values for population was at time 100 and the other one was at time 50, because one of the times was double the other time, this applies. We can use these formulas for finding P sub 1 and A. Okay, so this is, again, just a special case. Not always does this happen. In other times, if you would solve this system of equations with any method that you could that worked, and Newton's method would work for this one. Okay, so I won't do all the calculations here, but it's just really a matter of plugging in. And so if you plug in all your numbers that we know into these two formulas, you get P sub 1 is about 251.7812. A, plugging in all your numbers here, you get 0.0001210. So putting that all together into your logistic model function here, you have that the population at a given time is calculated using this equation. Okay, so kind of a lot to take in as far as how the equations looked in our examples, but the process, just take your time with it. And if it's population, use our given models if they apply. If there's no given model, then you do our process that we went through during our first two examples, and just take the steps to solve your differential equation, and then solve your function. And then depending on what the question asks, a lot of times they're asking you about time, a specific time, but sometimes the question stops at finding the function. So just pay attention to what the question asks, and then take your time answering it. All right, that's it for this one.